All right, so let me go about the final proof today. But you will see pounds. Then determining whether or not 2 is a square on P. This is squared minus 1 over 1. If P is 1 or 7 on 8. And minus 1 is P is 3, 5 mod 8. So we'll start with that today. And also, and talk to me after class. Conjecture is mostly true. We're gonna have a problem for you. And here's the famous quadratic reciprocity. All right, so I'm going to give a miss to part 1 because we've already kind of discussed that really. And we'll get busy on part 2. So we're going to assume here FP is the field of P elements. ZP, if you want to be more comfortable with it, and FP is the output. And if you haven't seen the field theory and stuff like this, don't worry too much. All FP is it's a field that's so big that, well, so big minimal in the sense that any polynomial with coefficients in FP has roots there. You can extract roots of any polynomial you want. Let omega in FP be a primitive eighth root of 1. Well, that means that omega to the 8 equals 1. That's root of 1 part. And omega k is not equal to 1. Or that is to say that 8 is the smallest positive integer power of omega that gives you 1. So, as we pointed out last time, if this is the case, then omega 4 must be minus 1, because in particular omega 4 squares to 1, and by the primitivity of omega, it has to be this has to be minus 1, unless there's a smaller power of omega that gets you 1. So in particular, well, what we're going to do now, I guess, is note omega squared plus omega minus 2 is equal to 0. Yeah, that's right. It's 0. And this just comes from manipulating this, right? Because omega to 4, 0, and now multiply by omega minus 2. and we're gonna let Z that is, equal omega plus omega inverse. So, notice that Z squared is omega squared plus omega minus 2 plus 2 times the product of the 2, which is 2. So what we found is Z is actually essentially the square root of 2 in this field, right? Now consider ZP, and since this is a field with characteristic P, we have the freshman's dream. So this is omega P plus omega negative. So let's consider first the case where P is equivalent to plus or minus 1 mod A. So in other words, this first case here in statement 2. So what does this give us? In this case, if you look at Z to P, well, replace P by what it is. This is omega to the plus or minus 1 plus 8K plus omega to the minus or plus 1 plus 8L. And in particular, omega to any multiple of 8 powers is 1, right? So this is really omega to the plus or minus 1 plus omega to the minus or plus 1. Agreed? So this is equal to omega plus omega inverse. And omega plus omega inverse is Z. Right? So in particular, what happens here is Z to the P is itself. Right? So, and of course, let me point out the obvious that Z is not 0, right? Because factor squares is 2. So Z to the P minus 1 should equal 1. Everybody okay so far? Now let's look at P. Well, what this is this is, in fact, y'all remember earlier we had that result that as long as this thing is relatively prime to P, then AP is equivalent A to the P minus 1 over 2. So this should be 2 to the P minus 1 over 2. But of course, Z, or I'm sorry, 2 is, what is 2? It is Z squared. So this is Z squared P minus 1 over 2, which is Z to P minus 1, which is so we've totally commented that case. Right? Okay, so on the other hand, now suppose the I'm sorry, P is equal to plus or minus 3 on A. So that is the second case up here. In this case, so kind of following our nose, doing, we did 4. What do we get now? We get z to the p is omega to the plus or minus 3, we'll say k, plus omega to the minus or plus 3 plus 8L. And again, we get the same sort of business with the 8's, right? Because omega to any multiple of 8 power is 1 because it's an 8th root of unity. And so this boils down to which actually is equal to minus C. Now, there's a bit of a reach on that, so let me justify that step. It was easy enough to see that over here in this step, Z was equal to this because that's how we define Z, right? This one's maybe a little bit more not quite so clear, but let me point out that if you look at omega cubed plus omega minus 3 plus omega inverse. Well, actually, let me start this one. Let's go omega cubed plus omega minus 3 plus Z is omega cubed plus omega minus 3 plus omega minus 1. Right, just replacing this. Z is. Now, see how I want to group in here. So this is omega cubed plus omega inverse plus omega minus 3 plus omega plus straight up omega. And so I'm gonna pull out an omega minus 1 here, leaving me with omega 4 plus 1. Right? And I'm going to pull out omega here, leaving me an omega minus 4 plus 1. Right? But notice that omega to the 4 is equal to minus 1. And if you take the reciprocal of this, omega minus 4 is minus 1 as well. Right? So this is a big fat happy minus 1. Both of these two are the same, both minus 1. So this is minus omega minus 1 minus omega minus omega minus omega.
Things in the parentheses are just 0.
Oh, not bad. Yeah. This isn't 1, this is 0. Right, there's certainly the same thing and there's 0. Thank you. Much better. Everybody okay with me? Right, because, there's the equation and all. So this means that omega cubed plus omega minus 3 plus Z is equal to the big fat 0. And so omega cubed plus omega minus 3. And so that should justify this step right here. Okay, so. Let's see what we get now, doing the same kind of thing that we did before. Now two P is two P minus one over two. And again, this is C squared. Which is minus one. Because since Z to the P is equal to minus C, I should put this down, Z to the P minus one is minus one. By Z, so we've got the same piece. That's really cool, but it kind of, you know, these primitive roots of unity, they've got these nice symmetric, the ways their roots behave are really kind of beautiful and works out nicely for us. Okay, so now the only thing we've got left is the famous statement of quadratic reciprocity. But to prove this, I'm going to need to generate a little bit of machinery first. We're going to look at something called Gauss sums. Any questions? Okay, so moving forward in the proof. Well, this is sort of like a little intermission before the proof here. So we're going to take a break and develop some limits here. I am going to denote is a primitive this is a primitive P through 1. So again, and P is usually prime, but you can define this in general for any n, and P to the K is not equal to 1 for K between 0 and K. So there's your primitive P through 1. If you're in a field of characteristic 0, you might think of E to the 2 pi over P, for those of you that are fans of complex variables and so forth. I am also going to assume I'm gonna be a Sith here and embrace the larger view of the force here. I'm going to assume that this 0 if P divides A. So sometimes I've done this, sometimes I haven't, but I'm not going to assume that A is relatively prime to P. This is just like the ordinary Legendre symbol if A is relatively prime to P, but if P divides A, this is like 0, and I'm going to assume the symbol takes on that value. So let me give you our first lemma. So let's look at this sum. N equals 0 to P minus 1. Sum this is equal to P. Sum this all up. This is equal to P if A is equivalent to 0 mod P. And by the way, that's not a huge, I can do that one in my head, right? Because if A is equivalent to 0 mod P, then that means that this thing is multiple P. Right, which means that this thing is always one, so you're just counting one P times, right? No shockers there. Anybody want to guess what happens if A is not equivalent to zero mod P? What's the guess?
Zero.
That's a great guess, and in fact, it's true. Yeah, so, and actually, one easy thing to do, you might think about it this way, is, what you're doing is you're adding one in the primitive P roots of unity of, in the case that A is, for example, one, you're adding them all up, right? And so here's the kind of intuitive thing. For example, if you take A equal to, one, then you have one plus this. And these things all in the sum, there's P of them. These are all roots to this equation. You've got the silly one, and the rest of them are the more complicated ones. They're all kind of symmetric. And so this should factor as x minus one, x minus first one, x minus second one. Well, and in fact, let's do this. These are all roots of this, which is oh yeah, I'll just call it right here. So these are all the roots of this, and right. So this should be so when you multiply this back, because these are all the distinct roots of this polynomial. Very cool, isn't it? So do you know where this comes in and putting this back together? That is correct. If you multiply this out, this is x to the p, because there's p. Right? And now you have the coefficient of x to the p minus one of something, right? Well, how do you figure out coefficient of x to the p minus one? Well, you have to take p minus one x's and one of these things. So the coefficient should actually, up to a sign, be this thing. But the coefficient here is zero. So that's essentially what's going on here. Let me do something more formal here. So, proof. If A is equivalent to zero mod P, then and so this should equal the sum n equals zero minus one, which is so that one we can brush aside fairly easily. If not, so if A is not equivalent to zero mod P, then let's write this sum. Oops. We write this out explicitly. This is one plus tornado to the A plus tornado to A plus tornado to the P minus one down to A. Right. And this is 1 minus. Correct. This is just the old thing from like some of your geometric series. This thing is not 0, and that's important because A is not equivalent to 0 mod P. That's crucial there. So this makes sense, but of course this one equals 0. So we're going to see. Okay. Here's another little short lemma to put in our tool belt. By the way, you all ought to jump all over this. What should this be? Oh, by the way, let me clarify. This is the Legendre symbol. I'm not adding up binomial coefficients. Just for clarity. What should this come to? And remember, it's important that P is a non-prime. So this actually sums to 0. Proof. What this is this is the first term is that Legendre symbol plus 1p plus 2p plus p minus 1. Now this piece is 0 because we defined it that way. And there are even number of terms here. Half of elements of non-zero elements of Z mod P are squares and half are not. So this is some sum of 1s and minus 1s. And I don't know exactly how it turns out, but I know that there's exactly half of them being 1 and the other half being minus 1. So this should just be a big flat accordion that collapses down to 0. Are you okay with that? Okay. All right, here is a definition. We define a quadratic Gauss sum be a sum of the form GA for Gauss, I suppose. The sum n equals 0 to p minus 1. The Legendre symbol in P times your so notice this is a parameter that depends on A. So it depends on A here, right? And A is basically the power of the primitive P3 of unity that you decided to augment with power of n. right? So when you say G of A, really the parameter is this A up here, the exponent here. So here are some properties of Gauss sums. And we're going to use this as a big tool for establishing quadratic reciprocity. So here is the first property I want to talk about. So here's this is like the dude's rug. It kind of ties the room together here. This sort of puts everything on one footing. This is sort of like all logarithms are essentially natural log, right? GA is so basically every one of these GAs, it doesn't matter what it is in terms of G1. So just doing the primitive infinity here. Let me make another observation here. Well, can somebody use this to make an observation? That means that essentially all Gauss sums are the same vary by sign or it's zero, right? Because this multiplier here can only take on the value 0 plus or minus 1, right? So that's very limiting on that sort of shows that they're kind of tied together pretty tightly. Proof. Suppose first A is equivalent to 0 mod. It suffices if GA is 0. Well, to this end, let's see what happens when A is equivalent to 0 mod P. Well, in this case, each one of these animals is 1, right? And so GA is the sum of P minus 1 of NP times 1. And this by lemma, whatever was 4, 2, 3, this is 0. Because you're just adding up the Legendre symbol as you go through modulo P. Well, if A is not, now suppose A is not equivalent to 0 mod P. In this case, what I want to do is I want to look at AP and of course, since A is not equivalent to 0 mod P, this multiplication is not annihilating stuff because that AP symbol is not 0. This is in fact P+1. Anybody see what we did here?
Multiply the Legendre symbol on the outside inside the.
Okay, right. So when I multiply this through, comes A N P. Right. This is a property of the Legendre symbol that APVP is equal to AB P, right? Everybody okay with that? And notice that none of the results, none of these things are zero unless n is zero, because A is not zero mod P. Everybody okay with it? Okay, look at me, I'm all fancy, I've rewritten it. How does this help?
Since A is not equivalent to zero, then that's just reordering of the things.
Since A is not equivalent to zero mod P, this is a reordering of right. So this sum and this sum should be exactly the same because AN goes through all these values only once, right? This sum and this sum are exactly the same, they're just perhaps written in different orders, unless, for example, A is one, but A is two, it just kind of reorders things. So this sum is actually the same as this. Is everybody clear on that? This. And so APGA is G1. Multiply again by AP and I get GA is AP G1, which is the way I stated it there. Okay, any questions on that? Okay. Right, okay, so let me make an observation here. It might be useful as well. If A is not equivalent to zero mod P, then if you take the Gauss sum A and square it, this is the same thing as AP squared G1 squared. Right, we're just essentially squaring both sides of that equation there. And this is always one. Right, whether, because A is not equal to zero, so this is either plus or minus one, we square it, it's always one. So in other words, as long as A is not equivalent to zero mod P, if you take any of these quadratic Gauss sums and square them, it's the same thing as squaring that. So in other words, they all vary by a sign, which we kind of observed a little bit earlier. Here is another lemma. Six. The lemma here says G1 squared this actually is minus one to the P minus one over two. Yeah, that's a type. let me make sure this works out. So this should be minus one P. Now. Oh, yeah, but there's like this. Okay, I've got it fixed. So, in other words, do y'all remember when we did so the first thing we did today is we did the symbol two P, right? And along our travels, one of the things that we did is, and remember, we were sort of focusing on two there. At one point, we had that crazy Z thing, and we said, oh, look, Z squared is equal to two, right? That was kind of a central piece of proof. This is the analog here. This is sort of the analog here, because what this says is if you take the Gauss sum one and you square it, it's P up to a sign, right? So depending on what P is mod 4, this is either plus P or minus P. So basically, G1 is a square root, it's the square root of P or minus P, whatever is appropriate here. And this is going to be useful for us moving down the road. Okay, so let's go through the proof of this. So A. So suppose that A is not equivalent to 0 mod P, then GA, G minus A. Well, what is this? This is AP minus AP. Great. And so, of course, this is going to be minus A squared P, which is the same thing as minus 1P. And so, when I take this, I get G1 squared. So when I take A minus A, I get G1 squared. Again, perhaps up to a sign, depending on what P is, mod 4. So let's sum this up. So if you look at the sum, A is not 0 mod P. So you sum mod P over all the non-zero elements. So basically you're summing from 1 to P minus 1, if you will. This is minus 1P times G1 squared P minus 1. Which is also the sum over all. Because the 0 doesn't make any difference, right? So we can actually do this way. Let's also notice that we're gonna write, let's see, I'm gonna write this G. GA is equal to. E X 0, P minus 1, G minus A, same on sum of Y. So writing that way, let's kind of multiply this out. So G minus A is equal to the product of these two sums. So, 0 XP sum P minus 1 like 0 YP. So let's group that sum together, and I get the sum over XY. I guess this would be. And it should be the tornado to the A X minus Y. That's, yeah, that's fine. I think it might be convenient. I know it's supposed to keep it separate, but it doesn't matter. Let's see what it can get here. This is A X minus Y. So, given this, all that we've collected here so far, when you sum GA, G minus A over A is not 0 mod P. This is the sum over A is not 0 mod P of the double sum, right? This big mess that we've got. Sum X, sum Y, XPYP. So you're summing each one of these double sums over the elements A that is not equivalent mod P. Rearranging the sum, this is sum of X, the sum of Y, XPYP. Times the sum. A is not equal to 0 mod B. A X. So that's just rearranging the sum here. And this is the sum over X, sum of Y. And what does this turn out to be? I'm going to write it this way. Notice what you're doing is, oh, yeah, probably put more here. This is XPYP. what is this bit right here? Well, it depends on whether, A is, oh, actually, I'm sorry, this one should be A is equivalent to 0. Because I can interchange these. What happens if A is equivalent to 0 mod P? This is a P. And if A is not equivalent to 0 mod P, it's a 0, right? So I'm gonna write this is either P and this is delta XY. Where delta X Y is delta XY is actually P inverse sum n equals 0, P minus 1. A X minus. Oh, I'm sorry. Yeah. And this thing turns out to be 1 if X is equivalent to Y mod P. Because if X and Y are the same mod P, and this is a 0, and these things are all 1s, right? And when you add this up, this is P divided by P inverse is 1. And it is 0 if X and Y are different mod P.
It's the Kronecker delta for.
That's right. That's essentially Kronecker delta for this thing. Okay, so we are at a place in this. I want you guys to look at this, make sure that you can digest it, sort it out, and we'll go back a little bit, clear this up, and come through this next time. Any questions for right now? All right. Well, I will catch you all on Friday. Oh, it is Wednesday, isn't it?
Yeah.
Yeah, Grant's giving a talk on numbers, right? I mean, that sounds pretty exciting to me, so it should be a fun talk, so encourage you all to be there.